Well, this is Tony Paul, and we're going to look at a simple piping example using FEPipe. I've already built the model, so I'd like to bring it up and plot it. Here's our piping system. We start at node 5, go up into an elbow, over into another elbow. This elbow has a stanchion support. We go into a plus Y support with friction, over to another elbow, down into an intersection, 2 elbows, and then into 2 receiving vessels. So this is the system we want to analyze. Appendix D of the piping code doesn't give me Sifts and flexibilities for the stanchion with the elbow, so I want to generate those. FEPipe has a program called FEBend. It's very similar to Nozzle Pro. I put in the bend outside diameter and wall thickness, the bend radius, the stanchion diameter and wall thickness, and press Run FE. The software generates the finite element mesh, Sifts and flexibility load cases. Here's what the results from the out-of-plane Sift case look like. This is a typical Markle loading case. One end fixed, opposite end free, other end loaded. You can see this is clearly the out-of-plane load deflection case. From the finite element result, the software can calculate the Sifts and flexibilities. Here are the flexibilities. We see that the computed FE, KI, and KO values are 5.5 and 6.3. The code calculated KI and KO values are 7.9 for both KI and KO. The code doesn't differentiate between KI and KO. So adding the stanchion reduces the flexibility of the bend a little bit, as we would expect. Here are the calculated stress intensification factors. The bend in-plane stress intensification factor from the finite element calculation is 4.2. The out-of-plane stress intensification factor, 2.4. According to the code, the in-plane stress intensification factor is 2.5, and the out-of-plane stress intensification factor is 2.1. As we said, the code calculation doesn't include the effect of the stanchion. So all general software packages now, even though you put a stanchion on a bend, still must include the stress intensification factors and flexibilities as if the stanchion wasn't on the bend. As we can see here, the in-plane stress intensification factor is intensified almost 2 times by the presence of the stanchion. So we'd like to increase the stress intensification factor and reduce the flexibility factor as per the finite element calculation in the beam analysis. So we go back to our beam model, and for the bend at node 15 at 0.16, which is going to be at 0.45 degrees or at a 0.45 degrees along the bend, we're going to put in the in-plane, the calculated in-plane and out-of-plane stress intensification factors and the slightly reduced flexibility factors. So now we've got a better model for the bend with stanchion. We're going to use standard intersection models for the intersections at the vessel head connections and for the pipe-to-pipe intersection, cylinder-to-cylinder intersection at node 35. So let's make that calculation and see what the code tells us about stresses in the system. Calculation's finished. We check. We'll generate a sustained stress plot. Software generates 3-dimensional stress plots where the nodes are produced as small squares and the allowable is the yellow surface that you see. So here are the sustained stresses. Node 40 is just under the allowables, and the node, or the intersection at node 55 in the vessel head, is just over the allowable stresses. So for sustained stresses, we're over. We'll take a look at the expansion stresses. For the expansion stresses, here's the allowable surface, shown here in green. Put the nodes on it. Node 40 and 55, which are the two nodes that are represented by the nozzles at the top of the vessel head, are over the allowable surface. So we've got sustained stress violations and we've got expansion stress violations. We know that when we use the standard B31.3 models, we get no flexibilities for the intersections or for the vessel heads. FEPipe allows us to use FEA control for both our pad reinforced cylinder-to-cylinder intersection and for our unreinforced nozzles at our dished heads at node 40 and 55. So under program control, we're going to use FEA solutions now for all three intersections in the model. I do that by changing the intersection model option from standard to advanced. And now the software will use finite element solutions for the cylinder-to-cylinder intersection and for the nozzle to vessel head connections. We rerun the model. Go back now to the three-dimensional plots for the expansion stress. With the flexibilities included, we can see now that all of our nodes are underneath the expansion stress allowable surface. Let's go check our sustained stresses. And we can see that all of our sustained stresses are under the sustained stress allowable surface. Adding the flexibilities reduces the loads in the system. Reducing the loads reduced the stresses and allowed us to become, or showed us that we are indeed under our allowable stresses. FEPipe produces the typical types of output. There's a beam calculated properties report. In this we can see that here's the intersection node identified as node 35. Tells us that it's going to use FEA calculations to determine the Sifts and flexibilities. Here's the Sifts and flexibilities that were calculated from the finite element analysis. Repeats that for node at 55 and 40, where we've got a dished head, unreinforced fabricated T in a dished head. Here are the dished head characteristics. Here are the Sifts and flexibilities from the finite element calculations, and also for node 40. Output is as expected from the finite element calculation. There's pipe properties, displacements, forces and moments, code compliance, and any overstressed nodes. Here's the forces and moments report, typical report for all the different code load cases. Here's the pipe properties report. One thing we note here that's different in FEPipe, for a typical B31.3 analysis, we only get from B31.3 Appendix D the in-plane and the out-of-plane stress intensification factors. The finite element program calculates both an axial, in-plane, out-of-plane, torsion, and pressure stress intensification factors, and all those are used for the intersections developed in the model. You'll notice that the branch and the header stress intensification factors are different, as they should be, and here are the stress intensification factors for the vessel heads. Here are the flexibility stress intensification factors for the bends. The displacement report, again a typical displacement report. Code compliance reports, typical code compliance reports as echoed in the plots. And overstress reports, and as echoed in the plots, there's no overstressed nodes in these models. And this is the typical way that you'd run FEPipe.